Good afternoon. I hope you're all nicely wired on the sugary donuts. We've got quite a bit of stuff to get through. So let's start talking about physically based rendering, or PBR, if my thing works. There we go. So this afternoon, we're going to start talking about how to basically get some content on the screen with Qt3D. This is going to be extremely brief. If you want more details, you should have come to the course yesterday or the talk just before this one. We're then going to go on and describe physically based rendering in a bit more detail. And then right at the very end, we'll pull the two bits together and we'll show how to implement physics-based rendering with Qt3D. So if you want to draw something with Qt3D, we have this thing called an entity component system, which is a little bit different to what you would find with Qt Quick, for example. In this case, we have an entity, which is basically a do-nothing object, and we give it some behavior by adding on some components, which in this case is a torus mesh, which gives it some kind of physical shape, some information about its geometry. And we can set properties on there like any other object. And then we have a lovely named normal diffuse specular map material, which just rolls off the tongue. And this gives it a surface appearance. In this particular case, it's a bump-mapped texture, so it perturbs the normal vectors used for lighting. And if we do that, then we can often see an example, which if you went to the previous talk will look very familiar. Here's a donut. Okay, you can see it's got some lighting on it, some textures, and we can move things around. That's using one of the built-in materials, this normal diffuse specular map. Now, if we want to go a bit further, we need to start defining our own custom materials. And Qt3D allows you to do this very easily. And we do this with a material element. And what we have in here is, if we ignore the part at the top for now, and have a look at the effect is where it actually specifies what shaders this is going to be using on the graphics card. Now, within the effect, we have the render pass and technique. Don't worry about that for now. This is more higher level stuff if you want to make your stuff cross-platform or do more advanced techniques. So in this particular case, we're loading the shaders from a couple of files called plasma.vert and plasma.frag. These are the vertex shader and the fragment shader, respectively. This is like a mini program that runs on your graphics card and does whatever we tell it to do in that program. And finally, the section at the top, the parameters, is a way that we can pass extra parameters or information through to our shaders, which, if you're familiar with GLSL shading language, it gets translated into uniform values. So if we were to use that material, we could see something completely different to our shaded donut from before. And that's basically all there is to making custom materials in Qt3D. Now, of course, the real trick is what do we put inside the shaders. Now, to do that, we have to do a little bit of maths, unfortunately. So we're going to, first of all, look at the motivation of why do we even want to do physics-based rendering. Well, traditional lighting models like Phong or BlendFong or Gooch and a whole variety of other ones are commonly referred to as ad hoc methods. They're not based on physical principles. And as a result, they tend to mix up lighting and material properties into the same set of equations. This can make it very, very difficult to take a material that you design to be used in one particular set of lighting conditions, say daytime, and then move it into a different set of lighting conditions, say nighttime, and expect to get sane results. Very often what happens is you end up making lots of horrible hacks, like adding additional lights with negative intensities and things to make your lighting look correct with that set of materials. And artists spend hours and hours tweaking this stuff, or programmers do if we have to do it ourselves, and it's horrible and not fun, and it's endless repetition. It's also controlled typically by non-physical parameters, so things like specular reflectivity coefficients and ambient reflectivity coefficients, which don't really map onto anything in the physical world intuitive to control. So these are some of the downsides of more traditional lighting methods. Now, physics-based rendering, or PBR for short, aims to address a lot of these issues. One nice thing we want to try and include in this is the concept of energy conservation. We can't have something reflecting more light than is hitting it in the first place, unless the object is an emissive object like a light bulb or something. But for now, we're going to ignore light sources. The whole underlying concept is we want to base our lighting model on how light interacts with matter in the real world, according to physics. As a result, we'll be able to control our materials with physical parameters that we can relate to in the everyday world, and it nicely decouples the lighting information from the materials, which makes our materials reusable under any set of lighting conditions. Oops, too far. So let's think about what is light. Now, if you've done high school physics, you'll be aware that sometimes we treat light as a particle, sometimes we treat light as a wave, sometimes we treat light as this weird thing called a wave packet, which is basically a photon. So for our purposes today, we're going to think of light as a flow of photons, particles. Now, we still need to consider wavelength, which is a property of wave-like motion of light. And at the bottom there, we can see a couple of relationships you may be familiar with, where we have the frequency of light, nu, is equal to the speed of light, c, divided by its wavelength, lambda. Or conversely, lambda is c over nu. Now, light carries with it some energy. And if you do a bit more physics, you'll find out that the energy Q can be written down as this little expression h nu, where in this case, h is a fundamental constant known as Planck's constant. So Q is our amount of energy carried by some light. Now, there's another related quantity called the radiant flux, which is basically the energy per unit time. And that's measured in watts. So this is just like how many watts does a light bulb kick out. Yep, that's how much light energy your light bulb was giving off. Now, we get a little bit more complex. We have to think about something called irradiance. Now, consider photons, particles of light, all passing through a little area in space perpendicular to the direction the light is traveling. The irradiance is the density of radiant flux with respect to area. So E is this d phi over dA, and it's measured in watts per meter squared. Now, this is what we think about when we have light shining onto a surface. So it's a measure of the flow of light onto a surface, so it's going to be something quite important to us. Now, just to give you a concept of scale, the sun shining brightly on a nice hot summer's day, if you measure a square meter on the Earth's surface, we have about 1,000 watts hitting that square meter. Okay, the sun is actually pretty damn bright, even at this distance. Now, intensity is related to these quantities as well. So the radiant intensity is the radiant flux per solid angle. So if you see there, we have a picture of a light bulb. If we pick a direction going away from that light bulb, the intensity is basically the flux in that little area. Now, if we were to integrate that intensity up all over the entire sphere, i.e. over 4 pi steradians, we would get the overall radiant flux. Now, and that's measured in watts per steradian. Almost there through the horrible bit. Now, intensity versus irradiance. If we have a point light source and we draw concentric spheres around it, then obviously as our piece of light, our photons move away in a certain direction that we're measuring in for our irradiance, for the intensity, then as we move further away, our solid angle covers a larger and larger area. Yep. And the constant of proportionality here is actually the intensity. So we can relate the intensity versus the irradiance with I equals ER squared. And that's, again, watts per steradian. It's the same thing, just a different way of thinking about it. And finally, we have radiance. Now, this is what detectors, such as cameras and eyes, actually measure. This is what we're sensitive to, or light meters if you're into professional photography. So we need to consider both the area over which our light is spread and the direction in which it's going. So there's some relationships down the bottom there. So we have radiance, L, is either the intensity per unit projected area, or it's the, forget the name, the intensity over solid angle. Now, where does this projected area thing come in? If we have a light source shining straight down onto a surface that's orthogonal to it, we take the full set of light. If we have light coming in at an angle, then we have to obviously take a cos theta factor into account because we're not getting all of the flux through that area. So we can consider the projected area. Now, so far we've been talking about purely physical quantities. However, perception is critically important for rendering. Now, there's a couple of fields called photometry and colorimetry, which, if you're interested, go read the book Real-Time Rendering. Lots of gory details in there for you. But the long story short is, when we're rendering, we can get away with using red, green, blue triplets for representing colors. If we were doing this properly in a full-blown physical simulation, we would actually have to use the full spectral energy density to model this. But because the human eyesight is so lossy, for any given spectrum, we can basically compress that down into 3 values representing red, green, and blue. And we can't tell any difference. We are primitive. Now, the good news for us is this is much, much cheaper than rendering the full spectral power distribution and having to consider that. We just use a 3D vector. So that's really good news. Right. This is a very important equation. So even if you forget all the previous stuff, try to remember this guy, the BRDF. It's the bidirectional reflectance distribution function. Yep. I'm sure you'll all remember that tonight after a few beers. Now, what it basically says is, if we look at this equation, we have a function f, which is a function of the light direction L, our viewing direction v. Yep, so we have a light over here shining down on me, so that would be my L vector, and you're looking at me, so that would be the v vector, because you're looking at me. Now, given those two vectors, we have a function that says, for all the light coming in, how much of that light gets reflected out to what you can see. Now, if we're considering point lights, which is good for real-time rendering, turns out things are very simple. I say very simple. They're simpler. We don't have to worry about nasty integrals and things. So for point lights, our solid angle that we're considering is 0. It's just 1 pixel out there corresponds to 1 pixel over there. So we can get away with all these nasty integrals, and we can just use discrete sums instead. So then our BRDF function then just becomes f is this L naught of v, i.e. the light that's coming into me, the irradiance. And on the denominator there, we've got EL cos theta I, which is, sorry, no, LO, I've got that back to front. L0, L out, is the radiance going out compared to the energy coming in, which is EL cos theta I. And cos theta I, we can calculate very nicely as the light vector, i.e. the vector pointing up to the light, dotted with my normal vector, which for me here would probably be pointing that way somewhere. So take the dot product between the two, that gives us that cos theta angle. Whoops. And if we rearrange that slightly, and then we sum up over n lights, rather than just considering one, we get this little guy here called the shading equation. So that's basically saying that the light you can see reflecting off me, LO, is the sum of the BRDF multiplied by the amount of light coming in from all the different lights, and then we just add them up. Now that strange operator in the middle, the circle with the cross in, is just a component-wise multiplication. So the light source, EL, would be a red, green, blue vector, and inside the BRDF, we would calculate that in terms of red, green, blue vectors as well. So we do a component-wise multiplication. Multiply those two things together, add them up over the number of lights, and we get the light that you can actually see. So that's what we're going to implement in our shaders. Now, the BRDF is a little bit of a tricky thing to understand when you look at it just as a differential. It doesn't really make much sense. But let's think about it and see if we can visualize it. So what we see here on the right is a little picture from a small application I found which allows you to visualize BRDF functions. So on there, the turquoise line is the incoming light, and it's hitting a surface represented by that grey plane, and then it's reflecting out in various directions with different amounts of strength. So it's like a probability distribution. Now, the green hemisphere on there is a diffuse term. It's called the Lambert function, which basically says light shining on a rough surface is going to scatter equally in all directions. So we get a nice hemisphere distribution. The red pointy out bit is the specular highlight. So if you shine light on a shiny object, you get a nice mirror reflection when you're looking down the reflection vector. So that's where we get a strong peak in our BRDF pointing in that direction. So this is actually a combination of two sub-BRDF functions, the diffuse one and the specular one. And there's a whole bunch of different BRDFs for different types of surfaces, depending on what your needs are. Now, later on today, we're going to look at one that covers most everyday materials, but if you're doing something special, you may need a special needs BRDF function. As an example of that, if you're trying to render the moon, you would use a BRDF function that instead of reflecting around the normal vector like that one does, it actually reflects light back along the direction it was emitted. This is why the moon looks like a flat disk rather than a curved surface of a ball. Yep, it's got very strong retroreflection. Now, we need to consider how light actually interacts with matter so that we can come up with a sensible form for our BRDF function. Now, there's three things light can do. It can be emitted, as in from a light source. We're going to completely ignore that in terms of objects we're trying to render. We're not rendering light bulbs themselves, only the things they're shining on. And the things we are going to consider here in green are scattering and absorption. Now, scattering is when light hits some particles and it changes direction. It doesn't change the amount of light there is, only which direction it's traveling in. And then the last case is absorption. This is where light travels through a medium. It doesn't change direction, but it does lose some of its flux. Yep, some of it is absorbed. Now, how does this occur in everyday life? Well, absorption is what we interpret as color. Okay, we have white light shining into something, and it absorbs some of that light, and it absorbs some wavelengths of light more strongly than others. And we see whatever is left, i.e. what isn't absorbed, as a different color. Yep, so here on that chart, you can see on the vertical axis, we have glasses of liquid of different colors because they have different materials in that are absorbing light of different wavelengths. And then the scattering is what gives these participating media different levels of cloudiness. So along the bottom there, we go from pure water to water with some stuff mixed in, all the way up to full-fat milk. Yep, they're all white because there's no absorption taking place, and we've got white light shining in on them, but they do scatter the light in many directions, so we can't actually see through them very well, and they appear cloudy. So that's scattering versus absorption. Now, if we start to consider ray optics, then materials are defined by their index of refraction, often given the symbol eta. Now, in the picture there, we can see a ray of light, some photons coming in, and hitting a optical discontinuity, a boundary between two materials. So in this case, the top one may be air, the bottom one may be water or glass or wood or whatever, doesn't matter. Some of that light will bounce off, it will be reflected. And some of that light will actually penetrate into the surface to undergo further scatterings or be absorbed, depending on what the material is. So that's reflection and refraction. And how much is reflected and how much is refracted depends upon the ratio of the indices of refraction. Now, there's two types of materials we're going to consider, metals and dielectrics, i.e. conductors and insulators, because they tend to behave very, very differently with how they interact with light. So, metals, first of all, they undergo surface scattering only. So if you shine light on a metal, a pure metal, it will reflect the most of its light. Any light that does get transmitted into the metal is immediately absorbed because metals have a sea of free electrons, and that very quickly gets rid of any light that penetrates. Dielectrics, on the other hand, conductors, they too will reflect some light at the surface, but any light that does penetrate and isn't reflected will undergo multiple scattering events and also some absorption events. So the different colors here inside that picture are supposed to represent some light being absorbed and changing color and then coming out again. And you can see because it's undergoing many, many scatterings in that surface, it randomizes the direction of the light somewhat. And then finally, there is a third type of material, semiconductors, but we're going to ignore that because we don't tend to render semiconductors in real time. So we have metals, which primarily undergo surface reflectance, and we have dielectrics, for which we also have to consider body reflectance. So two different things, two different types of material. It seems sane to have different terms for that in our BRDF function. So we have a specular term, which is our shiny highlights, and we have a diffuse term, which is more the matte color of objects that we see every day. And if you get really into this, then the distinction between the two terms can even vary upon the scale with which you're trying to render something, but we're not going to worry too much about that today. So, there was a very smart guy who discovered a lot of this stuff and wrote it down, called Fresnel. And if you want to know all the gory details of this, go and find yourself a textbook on optics. The equations Fresnel came up with are very, very complex, and again, based upon the indices of refraction. Now, what we have is light shining onto a surface, which we assume is optically smooth. Now, when I say optically smooth, that means any imperfections in that surface are smaller than the wavelength of visible light. Yep, the bumps and the nooks and crannies are not going to affect us adversely because the wavelength of light is much larger. And it's quite possible to polish things to that level these days. As an example, the wavelength of visible light is around 400 nanometers. The width of a single strand of spider silk is about twice that. So we can easily polish mirrors to that degree of accuracy. And we do it for telescopes all the time. Okay, so the Fresnel reflectance equations basically tell us that when we shine light onto a surface, how much is reflected depends upon the angle with which it hits the surface. Now, you can actually see this in every day-to-day life. So if you look at an object at a very glancing angle, and there's a light source behind it, so the light source is hitting it at a glancing angle as well, you can see that light source reflected in it, even if it's something you would think is rough or matte, like a sheet of paper. You can see it very clearly if you're stood by the side of a lake that is still, and you look over the surface of the lake, you see the sky reflected and the trees reflected. If you were to go up in a helicopter and look straight down at the lake, you would see down to the lake bottom, assuming there's not too much scattering going on. So the Fresnel reflectance says how much surface reflection we get versus how much light penetrates into the body itself. And in this diagram, you can see the values for different types of material. So down at the bottom there, we've got water. Starts off with a very, very low reflectance when the light is shining straight down on it, and it rapidly increases up towards 1 as you get towards a grazing angle. And the other materials behave the same. They just start at a different value on the left-hand side there at 0 degrees. Now, some of those materials, like aluminium and copper, actually behave differently for the red, green, and blue channels that we represent them with. So that's why they have 3 lines rather than 1. So metals can sometimes have a colored specular reflection. Non-metals, insulators, dielectrics, tend to have monochrome reflections. Now, in real-time rendering, the equations of Fresnel are far too complex to calculate in real time, well, at least today, so we tend to use the approximation of Schlick, which is this little function here. That's basically saying that we can calculate the amount of light that's reflected based upon the incident angle of the light and this parameter RF at 0 degrees. So that's saying that if we choose a color that an object is when the light is shining straight down on it, we can use this simple function, which just does an interpolation, to work out how much light is reflected at any angle. Now that's actually very, very nice, because our artists can just come along and say, okay, yeah, that's gold. I know when I look straight down on gold, it's a gold color. I'm going to pick that from my color picker. For other materials, such as wood and cardboard and plastic, we would choose a very, very low value for RF0, because remember, our dielectrics are right down the very bottom of this graph. They have incredibly low values. Metals are much higher, like 0.5 or above. And that's actually pretty accurate for most materials. So that's good. And here's some examples of the different values for some different types of materials. Again, there's lots more of these you can find online and in papers. Very often we specify this in the sRGB color space, purely so we get more precision at the bottom end where lots of our materials occur, around the sort of 4% level. Now gold, you can see, third up from the bottom, is very, very strongly colored. It's not a gray color like the ones near the top of the table. Right, so whereas metals, for any light that penetrates the surface, absorbs them very, very quickly, dielectrics don't absorb everything. They undergo multiple scattering events as the photons go in and bounce around. So we also have to worry about body reflectance. Now insulators, some of them are homogeneous, so things like glass and water, they don't have any optical discontinuities inside them, so they appear to us as transparent. Other insulators, such as wood, which has a very fibrous structure, or cardboard or plastic, they have lots and lots of optical discontinuities inside them. So every time we see an optical discontinuity, remember we get some light is reflected and some light is refracted. So I've got a picture of a beer up there for two reasons. The first reason is I like beer, and the second reason is it's a good example of how these optical discontinuities can change the visual appearance very, very much. So the beer itself is obviously made from beer, but so is the head on top of the beer. The difference is that the head on top of the beer has lots and lots of optical discontinuities because it has beer, air, beer, air, beer, air, as you've got all these different bubbles. So what happens is the light enters into the head of the beer, undergoes a scattering, changes direction a bit, passes through a bit of air, and then hits some more beer, which is another discontinuity, scatters again. And each time it goes through a little bit of the beer, it gets absorbed a tiny bit as well. But because it's very, very thin bubbles of beer, the absorption is tiny, negligible. So the light gets scattered many times, but absorbed not really at all. So the head of the beer is very bright, because we're not changing the amount of light very much, and it's white, and it's opaque. Yep, because we've undergone lots and lots of scattering events. We've jumbled all the information up. The body of the beer is more homogeneous. The light passes through it. It doesn't get scattered, but it does get absorbed, so it changes color and becomes this lovely golden hoppy color, which I'm going to drink some tonight. So, body reflection. The diffuse color is driven by the absorption happening inside the material, and it can be very, very different from the Fresnel surface reflectance color, this F0 thing we were talking about, RF0. The most common diffuse BRDF is the Lambertian one, which basically just says light is scattered equally in every direction. Very simple. So we just say there's a color, C diff, and we divide it by pi to take into account its spread over a hemisphere. There are other diffuse BRDF functions available, such as the Disney one, which is used in the Disney Pixar films. That's fine for offline rendering because it's quite expensive. It's still a bit too expensive for real time, although it is now starting to appear in some real-time games as well. Oops. Back. Yep. So, now we got into microfacet theory. So far, we've been assuming an optically smooth surface. Now, surfaces, as you know, in the real world aren't perfectly smooth. Even if you go down to the sort of nanoscale, individual atoms cause lumps and bumps on a surface. Now, because they're less than the wavelength of visible light, we're going to completely ignore those. There is some research coming out at the moment which basically says perhaps we should be considering that scale of interaction and include diffraction effects as well, because it may actually add to some limb darkening and things as well on the edges of objects. But for now, we're ignoring nanoscale geometry. The macroscopic scale, i.e. everyday scale geometry that we deal with, we're familiar with how to render that. We define a normal vector along with our vertices, and we include that in our shaders, and we can say, yeah, okay, the light reflects around the normal, job done. Turns out that's not enough. We also need to consider the microgeometry. So this is the imperfections on a microscopic scale. Now, when we're rendering, we don't tend to render things at a microscopic scale. We want to render them on an everyday scale, but we do want the light, the visual appearance, to behave how it should. So, when we're rendering, the size of one of our fragments, i.e. one of our pixels, is actually much larger than the size of the microgeometry. But the geometry within there, the microfacets inside this fragment are actually big enough that they would affect how light behaves. So we do need to consider it. And this is one of the main improvements of PBR shading over the old Phong type stuff. So, what do we have? We basically assume that a surface covered by one of our fragments is not just a perfectly flat mirror, like we would do in the traditional lighting model. We assume it's made up of lots of little tiny mirrors, all pointing in random directions along that surface. So just pop forward a slide. So like the top one there, or the bottom one on the right-hand side, we can see lots of little tiny, small planes if we look at it edge on. Okay, these are our microfacets. Now we treat each of those like we would an optically smooth mirror. So we say, yes, okay, they've still got nanoscale geometry, but we're not caring about that for now. So each one of those is treated as a Fresnel mirror. Now, the reflection vector, R, can be calculated from that expression there. And as you can see, it depends not just upon the incoming light direction, L, but also upon the normal vector, N. So if we got lots of these little facets all pointing in different directions, that means our reflection vector is also going to point in lots of different directions. Now, we've already said that our geometry here we're considering is too small to actually render it directly. So we can't resolve this, we're just going to treat it statistically. And to do that, we use something called a normal distribution function. So this is just a function that basically says, if I give you an angle for this particular fragment, you tell me what percentage of these microfacets are actually pointing in that direction. And we're only going to consider those ones when we do our lighting. So as an example here, we can see how the microfacet normal distribution function affects the reflection. So now we're talking about specular things. So we have light rays coming in. These are the yellow lines, and they hit our surface at whatever point, and then they bounce around the normal vector for that particular facet. Now, if our normal distribution function is, our normals all more or less point in the same direction as our macroscopic normal, we get a very nice, sharp, shiny highlight, as shown in the top left there on the object. If our normals for our microfacets are much more jumbled up, our reflection vectors from our little equation there also get much more jumbled up, and we see a much more blurry highlight reflection. So roughness is one of these things that matters and is something that controls this normal distribution function. Now, most materials have a continuous NDF. It would be a bit strange if they were discrete with breaks in continuity. So most of the ones we're going to see are continuous. Now, the strength of the peak of the normal distribution function is usually controlled by the smoothness, or equally the roughness, of our surface. So if we have a rough surface, our normals are going to be much more spread out. If we have a very smooth surface, they're all much more aligned, and the peak in our NDF is much stronger. Most materials have NDFs that are isotropic. They're the same in any direction. However, some things, such as brushed metal, actually introduce surface imperfections with a definite directionality. So brushed metal saucepans, for example, give you this circular pattern on the base of the saucepan. That's this microstructure causing the light to behave differently in different directions. Now, when we're talking about the normal distribution function, we have to consider this guy called the half vector, which is actually quite important. So again, we've got our vectors L and V. So L is our light vector shining on our surface, and V is our viewing vector, i.e. out to you guys. Then importantly, we should only consider those microfacets where the normal vector coincides with this thing, the half vector, which is exactly halfway between the vector between you and the light source. So if I was a microfacet, we'd only consider me if my normal vector was pointing in that direction. If it's not, we don't count it as part of our lighting equation. Now, when we've got geometry on this scale that we're not rendering directly, there's also other effects it can have on the behavior of light. So on the left there, you can see sometimes if we have little bumps and knobbles in our surface, it may block out some light hitting the surface somewhere else. So that's shadowing. Yeah, it's just like shadows you're familiar with. It's blocking out light to some parts. And then we have masking, which is where light has actually hit a surface and then reflected, but then it's blocked getting to you guys, the viewer, by something else that's in the way. And then finally, on the right-hand side, there's multiple bounces, which we just completely ignore in PBR at the moment. Yep. We know that's a deficit, but it just turns out to be too expensive. Now, some very clever people sat down and came up with a completely generic form of a specular BRDF, and it takes this form here. So the bottom one is more like how you would write it in code, because we use dot products and things rather than taking cosines using trigonometric functions. So what do we have? We have this function d. This is our normal distribution function. So that's basically saying that only those facets aligned with the half vector between the light and the viewer are the ones that should be considered. That's a value between 0 and 1. So we come up with a function that describes that percentage. We then have this term g, which is a geometric or visibility term. And that's saying, of those facets that participate in that reflection, what fraction of those are actually visible to the light source from the shadowing, and are then visible to the viewer from the masking. So again, that's a value between 0 and 1. And then finally, we have our good old friend, the Fresnel reflection term, which is basically just saying how much light is actually reflected at the surface, according to the incident angle. And then the terms on the bottom are just correction factors and constants to take into account the different coordinate systems involved. So that's a constant. Oops, where are we? So if we consider our traditional Blin-Fong lighting model with a diffuse Lambert term, we might have a BRDF looking something like that top line there, where C diff and C spec are our reflectivity coefficients we're familiar with. Now, if we want to include the Fresnel term in this, so we can try to interpret this as an actual microfacet BRDF, then we can just replace C spec with our Fresnel term. So rather than a user coming along and picking a C spec value almost at random that might be non-physical, we're going to use this RF value, the Fresnel reflectance. And now notice it's the reflectance value according to the half angle h. Yep, because we have to consider our microfacets, not the surface normal n. And then if we compare that to our microfacet specular BRDF, we can actually see that our normal distribution function is that term on the left, m plus 8 over 8 pi times cos to the power m of theta h. And our visibility term, our geometric term, is actually 1. Yep, so we're not considering masking and shadowing at all with this simple BRDF. Now, there's other BRDFs available that do have a very different visibility term. So that there's the Smith visibility term, which is often used in conjunction with a specular BRDF term called GGX. If you want to find out about those, just go have a look on the internet and Google. You'll find out lots and lots of stuff. So this is a very simple BRDF that we've kind of derived from our good old traditional Blin-Fong lighting model. And if we feed this back into our shading equation that we saw earlier on, we find we end up with something like that at the bottom there. So it's not as scary as it looks. It's basically just saying that we're going to sum up our incoming light source, so the EL times cos theta I. So this is the amount of light shining onto me from our light source, taking the cos theta factor into account for the irradiance. And then we component-wise multiply that by our BRDF, which is consisting of a diffuse term on the left there, C diff over pi. This is our hemispherical reflectance. And then on the second term there, this is our Blin-Phong specular term, which is that long red thing we saw on the visualization earlier. And we then iterate over that for each light, sum them up, and that's our resulting light color that we assign to our particular fragment in our fragment shader. Oops. Now, the one thing we haven't talked about so far is energy conservation. Now, when we did things with ad hoc models, we would come along and somebody would choose C diff and C spec almost arbitrarily so that your scene looks right for those particular lights. Yeah? It's not fun. Now, with PBR and energy conservation, we know what's going on a bit better because we've actually thought about it. Now, we know when light hits a surface, we have the Fresnel reflectance equation that says how much light is reflected and how much gets transmitted or refracted into the surface. So the surface reflectance gets first dibs on that light. So really, the specular term is the one that gets calculated first, and then the amount of light that's left available for diffuse reflection is basically 1 minus that percentage. Yep. The diffuse term may then attenuate it more by having more absorption, but the maximum amount it can be is 1 minus the specular contribution. Yep, so that's simple energy conservation. There's more advanced ways of doing this as well if you want to get into it more, but they're more expensive to implement. This is plenty good enough for us today. So just to wrap up, a quick summary of what we have to consider for PBR in terms of the theory. We have a shading equation that requires a BRDF. That takes the amount of light coming in and says how much light bounces off in every possible direction as a fraction. We have to consider diffuse reflection, which is body reflection. So light penetrates the surface, bounces around, some gets absorbed, some pops out again. Specular or surface reflectance is light hits the surface and bounces off according to the Fresnel. And then we have our microfacet theory where we consider the normal distribution function, which little faces or facets we're considering point in the right direction to be included in the reflection. And then of those, which ones are actually visible both to the light source and to the viewer. And then we consider the Fresnel reflection and energy conservation. That's quite a lot of stuff. But by doing that, we can then start to implement things. So if we remember back to our first couple of slides, we can make a custom material, and we can then parameterize our shaders based upon some of these quantities. So the albedo, for example, is like the diffuse reflectivity. A roughness contains how shiny or blurred our reflections are. F0 is our specular color, looking straight down on an object. And the metalness basically just says, is this a metal or is this a dielectric or something in between? Because you can have metals with impurities and things like that. Now, if we do that, we get something like this. So here we have our old friend Suzanne, the Blender model. And we've got some little controls at the top here that allow us to change some of these parameters. So you can see I've got some point lights sitting in the background. That's what these little blue spheres are. And as we move around, we can see the highlights on the monkey head. And we've got reasonable lighting on there. Now, if I start to change the roughness, we can see that the highlights, they get larger and they get dimmer. Yep, so that kind of mirrors reality. If I ramp the metalness all the way up to 1, we have no diffuse contribution whatsoever. It's only specular. Yeah. And if I then change the F0 value, let's find a color, yellow. Then this is 100% pure metal, because that's what we've set it to. and we get a yellow highlight. Now, we don't actually see pure gold very often under a point light, but that's what it would actually look like. Now, if we make it not pure gold by ramping down the metalness a bit, and if we chose a different albedo and increase the roughness a little bit, we see something that looks a bit more like gold that you'd expect every day. It still doesn't look great on the projector, I admit. But you can change these parameters quite easily to get all different kinds of materials, and we're not changing the shader at all. All we're doing is changing 2 colors and 2 numbers for the roughness and the metallic level. So how do we implement that? Turns out to be reasonably easy. We have a main function, main QML, which is just an entity containing a mesh, a transform, and our custom PBR material. And our PBR material itself is, as we saw in the slides, just a material. It has an effect. We've got some properties to expose to control these inputs. And then we load in our shaders. I won't go through the shaders in full detail because we're running short on time. But all the fun stuff happens in the fragment shader. And if we go down to the main function, we can see here we're starting off with a vec3 equals C linear. Now, it's very important to work in linear color space when you're doing calculations, not sRGB, because things don't add up properly. We're then iterating over each of our lights, and we're calling this PBR model function to add on the contribution for each of our lights. So this is the summation we saw in the shading equation. And our PBR model is just working out some useful quantities, so our light vector, our view vector, and the half vector. Simple. And then we just work out the dot products between them. We then call this function the diffuse model to get the diffuse contribution, and that's simplicity itself. It's literally just, that. Very simple. We just take the material albedo, and then we're multiplying it by 1 minus the material metalness, so we get the albedo from that. And then we're dividing by pi to take into account the hemisphere. So that's our diffuse factor. And then our specular, we just call this specular model function, which does our Fresnel function, our normal distribution function, and our geometric model, and then feeds that into the microfacet BRDF. Our geometric model, as we said, is just 1. Yep, we're not considering that at all. And the Fresnel factor is just the approximation of Schlick, and the normal distribution is just this good old Blin-Fong thing that we saw in the equations. So a handful of lines of code, and then we apply the energy conservation. Yep, so we've got 1 minus specular multiplied by diffuse plus specular. Multiply that by our light intensity and the L.n cos theta factor from the light source, and that's our contribution. And then finally, right at the end, we just apply gamma correction so it looks better on a display. So that's a simple implementation. Now we can go further. There we were just having constant properties across the entire surface, but of course we can use textures to encode this stuff. So we can use textures as inputs into our shaders. And then if we do that, we get something a bit like this example. So here we have a simple cube with some textures that represent the albedo, the metallic level, and the roughness. So as you can see, we've got 2 different types of square on there. If I zoom in a bit, if I can get the key combination right. There we go. So we can see some squares reflect light more than others. Yep, we've got different levels of metalness for those. And we can see we've just got 4 point lights in here, and we're getting the nice reflections with the elongated shapes you would expect. Yep, and if we were to do this in a more complete scene, the lighting would look very natural and it would fit in. So that's using exactly the same shader, except we're getting our parameters from textures instead of some constants. And if we go even further, instead of using point lights, we can actually use a cube map texture of the environment around us as our light source. So instead of taking a point light over there, we can say, okay, here's my surface. I'm looking at it there. I'll reflect off it into our cube map and say, that pixel up there is actually my light source for my particular fragment here. And if we do that, we can prepare some special cube maps offline by pre-convolving this stuff. We end up with an example that looks more like this one. Ignore that. What's happened there? Yeah, don't reopen. I don't know what that was. Okay, so here we have another material that I've made from some textures to look like some rocks, and we've got a cube map around it in the distance, and we're actually using that cube map as a light source to light our shiny wet rocks here. If I just bump up the exposure a little bit, you can see it all varies in sync. We've also added parallax mapping onto this as well. Well, Kevin did. And that means basically that you can see we've got some lumps and bumps on here. Parallax mapping makes that look much more realistic. So if I increase the height level, you can see we get these indentations go in and out, and it looks pretty good. That's actually a completely flat surface as far as the geometry is concerned, but by fooling the lighting equations, we make it appear like it's lumpy and bumpy, and things do get properly occluded. So there's all kinds of things you can do with this. And if we change the material type, of course, we get a completely different appearance. So we can go back to our other pattern. Where are we? There. And there we are with our other pattern. Oops. And you can see it fits naturally into the lighting environment because we're getting our light information from the environment. Yep, this is often used in AAA games all over the place. They generate these cube maps on the fly. So then the question is, how do we actually do some of these things? Well, you can generate these cube maps from an input environment map using a tool called LIS. It costs about £50 or something like that. Very, very handy, works on the GPU. And then it's also important when you get to that kind of stage to use high dynamic range rendering, because obviously the sun, we said, has an irradiance of like 1,000 watts per square meter. That's much bigger than the value of 0 to 1 we normally work in with low dynamic range rendering. And then if you're doing HDR rendering, of course, you then need to include tone mapping at the end, so we can actually display it and bring everything back down to this 0 to 1 range. And you can include exposure and all sorts of things, and as I say, parallax occlusion mapping. And then just to finish off, how do we actually make these textures for our PBR materials? Well, there's some very handy programs from a company called Algorithmic, called the Substance Tools, that allows you to both create these materials and then paint with them in 3D. And very nicely, these tools are written in Qt as well. So there's an image of Substance Designer making that checkered pattern material. So you have a little graph of nodes that create shapes and then create repeats of them and blending and distort them in different ways. And you can output these channels for the base color, the metalness, the roughness, and normal maps and things like that. It's very, very nice, very easy to use. And there's an image of Substance Painter where I've just painted a traffic cone covered in mud with a camera attached to it. Again, it's basically Photoshop for 3D. And it again can output these PBR textures ready to use. Okay, and there we go. Thank you, and any questions? If it's a hard one, you're fired.
Questions make you look better, I think.
Only if I know the answer.
This sounds to me like it should be some feature in Qt3D that shouldn't require me to write any shaders at all, right? It
Correct.
sounds like something you could have a class for. I want PBR material and just set the...
That's right, yes. It's something that's missing from our material set at the moment, and something we're hoping to add, hopefully, for 5.9.
Oh, okay, thank you.
What was the problem to getting to PBR shading from Phong shading? Like, why did it take so long to get there? Was it a graphics issue that the performance was not enough to render with PBR?
In terms of in general, or like just in Q3D?
Time-wise.
Sorry?
Time-wise, like 10 years ago, it wasn't used, right?
Yeah, I mean, to some extent, the graphics hardware hasn't been powerful enough until fairly recently. Real-time rendering seems to lag around about 10 years behind what they do offline. The PBR stuff they're doing offline now is just crazily complex. But now we can do this form of simple PBR shading in real time. It's not actually much more expensive than traditional Phong-type lighting, but what's really driven it the last few years is artists love it, because it's so easy to work with. You make some materials, you put it into your scene, and it looks great. You take that same material, put it in another scene, and it still looks great. You don't have to spend days or weeks tweaking parameters all over the place. Yep, you just say, it's this metal with this specular color, and I know I can put it here, here, and here, and it's going to look great. Any more? No, I've put you all to sleep.
Okay, thanks, Sean.
Oh, one from Passy. Uh-oh.
Yeah, just one question. What is the minimum requirement on the shading language side? So can you run this on GLSL, like in OpenGL ES2, or does it require OpenGL 4 on the desktop? Or
you can run PBR on ES2. The only bit on here that I've done today that wouldn't run on ES2 is looking up the image-based lighting. We use a mapped cube map for that, for the different levels of roughness for the reflection, and that uses the texture LOD function, which isn't available on ES2. So out of the box, that wouldn't work on ES2, but there's other approaches you can use to make it work on ES2. Yeah.
Not a cube map, but we pre-compute kind of a hemisphere onto a standard 2D texture. And in some cases, you can even put that into the alpha channel of another texture that would, sum up kind of nicely and fake it enough.